This podcast is on theory and application of regression analysis in multivariate cases. We will first have a look at the theory and the model of this multivariate regression, and then we will look at applications. The model of multivariate regression is best explained starting in two variables x and y. There we want to explain a third variable z as a linear combination of x and y. This means that we have a constant giving the offset, then we have a slope in the x direction and a slope in the y direction, and the whole thing is completed with an appropriate error term, such that the assumptions of the regression model are fulfilled. This error term epsilon I needs to be normally distributed with always the same variances sigma. So the variances for all points have to be the same. Now this means that we can fit a regression plane to our data. We have the z-axis that goes in this direction, we have the x-axis, and we have the y-axis. Now z is explained through x and y in a linear relation, and if you remember your mathematics course, then you will know that the equation that we have up here is exactly the equation of a plane in a three-dimensional view. Now we can even generalize that. We can say let's take more than just two variables. Let's take n variables, name them x1 to xn, it's easier than x, y, and so on. Now of course we cannot visualize this anymore, so this is something a little more abstract, and also the model looks a little more abstract. So we explain our variable zi through some kind of offset, which we call b, and then for each x, 1, 2 till n, we have a corresponding slope parameter that is fitted in the regression model. This is all different parameters, and this happens for each data point indexed by I. Again, the model is completed with an error term epsilon I, which has to be normally distributed and homoscedastic. This is the model of two-variate and general multivariate regression. Now, I have already mentioned the assumptions. Let's summarize them here once more. So the model has to look exactly as depicted in the box, with the error terms being normally distributed and homoscedastic. Linearity is a very strong assumption here. So parabolas, cubic functions, exponentials, logarithms, and so on are not taken into account with these models. Another assumption that is not so evident is the independence of the variables x1 to xn. This independence flows into the interpretation of the statistical results. If our variables are dependent, then the calculated p-values are usually too small, as they would be in reality, or in other words, confidence and prognosis bands will be too narrow. Now we can have some typical problems with these assumptions, since the model itself and the data as well is very hard to realize due to the high dimensionality, unless you have the two-dimensional case which is depicted down here. This I would call a typical problem. It's hard to visualize the data. The next difficult problem is what kind of relevance variables do we choose. So if we have x, y, and z, then it may be that z doesn't depend on x and y, but just depends on x. Or if x and y are very strongly related to each other, then z can already be explained through one variable, because maybe y is already explained through x, and then z is explained through x alone. If you continue studying statistics, you will maybe run into a thing called PCA, Principal Component Analysis, PCA regression is something to take away the dependencies between the variables, but we will not treat that here. Another typical problem you have is the scale of variables. It can easily be that on one scale you have fertilizer, which you measure in kilograms, and on the other scale you may have water that you measure in hectoliters, and on one more scale you have the hours of sunshine a day. So the scaling is not inherently clear. Should you take hours, should you take seconds, milliseconds, and so on. So this is a problem we can have. We will not talk about how to solve this problem. I would like to just sensibilize you for these topics. Now, one of the most difficult problems is the dependence of the variables or the independence. Here exemplified with x and y. We see that the data on the right side forms a line instead of a plane, so we can just directly do like this. But try to fit a plane through a line. This doesn't really work, right? So in this case it would be very, very tough to fit a plane. In other words, we can say if x is given, y is following directly from x, because, let's try. We give ourselves an x, then we are here, then y more or less follows. Due to this line property here, and with that you already determine z. So you can determine z with either x or y alone. All the information on z can already be encoded through y alone or through x alone, and this is the problem with dependence. You do not know how to fit the plane. You have a redundant dimension. Now let's look how we do this multivariate regression in R. The first is the structure we need to look at. So structure-wise, the two-variate regression is still visualizable with the library RGL. We already know this library. We can use the command plot 3D x, y, z, and then the three-dimensional points will be plotted. Be aware this works only for two-variable regression. Then we can, as we already know from the one-dimensional case, say linear model explains z through combination of x and y. You don't need any brackets or anything, so this suffices. This is not necessary, but could be done. With the command summary that you see on the right side in the box, you see what you get back. So what you get is you see, so first of all, the formula once more. Then you see some statistics on the residuals, which we will not use. We will visualize them immediately. And what is most important is the coefficients. So you see an intercept, the slope in x and the slope in y as estimate. For these estimates you get standard errors and you get p-values. The t-value is not important. We see here highly significant values in all three variables. Then you furthermore see that you have an adjusted R-square or a multiple R-square. So you see you take this one here, and this is the equivalent to the R-square in 2 dimensions. Again, you have f-statistics, meaning that you compare the whole data without any model, and you see, look at the variance, and then you look at the variance of the residuals, and if these variances are significantly different, that means your model explains some variance in the data, and this significance value of this f-test between the two variances, data and model, this p-value is given here. As I said, the information on the residuals is a little bit sparse up here, so we want to have a little more. That's why we use our IAS library once more. We can say source tests and visuals.r. There is now also a version for Macintosh available. And we can say visualize residuals of R standard of reg$resid, and reg$fitted is the values that you would like to have on the x-axis. You take the fitted values due to some mathematical reasons. You could also take any kind of numbered values and look for structure, but taking the fitted values will show you maybe a little more. So what you should see here is that the normality assumption is fulfilled, which is the case here. Both of these p-values are are way above 0.05. Then you have the residual plot, which should not show any structure, and you have the quantile plot, where the data should more or less lie on the red line for the normality assumption. So this is mainly for checking the assumption of normality and to assess whether the residuals are somehow structured, implying that your model may not have been the right model for this data. We will look at 4 examples: a regular case, a case with dependent variables, a nonlinear case, and some kind of big data extreme example. So a regular case we see here, it's 2-variate, so we could even by hand try to draw a plane through this data. If we fit our regression model, then it just looks as we have done before. The summary is very clear. All the parameters are highly significant. The R-squared is very high, and the model is highly significant as well. We do not see any structure in the residuals. The QQ plot is fine, and the Shapiro-Wilk as well as the Kolmogorov-Smirnov tests are okay. So we seem to have a good model which seems to be linear and have normally distributed residuals. Dependent variables. Visualized here, you see that the data is forming a line and not a plane. That means you have one redundant dimension. Here, if we do the same analysis, we observe that again the parameters are significant, x and y. And the normality assumptions are fine, and the structure in the residuals also looks okay. So that means our model would fit perfectly, but now be aware that there could be something wrong because you have dependency. Dependency doesn't show in these residual plots. Dependency only shows in so-called correlation plots, about which we will talk now. If the data here is strongly correlated, that means that those p-values are not to be trusted fully. It could be that they are way above what is displayed here because our data is dependent. Good. Let's look at the correlation plot to assess correlation between variables. If you use the correlation coefficient as you have learned in mathematics already, here correlation, you can do that also for several variables, but you need to bind all those variables into a matrix with the command cbind. So you just take your 2 variables, x and y, you say cbind of these variables, and then you put core in front, and that computes the correlation. That whole thing you save in a variable we will call core mat for correlation matrix, and then you need to load a library called ellipse. Remember, maybe you have to install the package first, but only when you do it the first time. In this ellipse library you have a function that is called plot core for plot correlation, and this needs to be fed a correlation matrix. And what it does is it looks at the entries of this correlation matrix and it plots a circle when the correlation is very low, and it plots more towards like an ellipse when the correlation is very high. So between x and x, it's clear that the correlation is 1. It's the same variable, so you just see a straight line telling you, okay, there is correlation. Between y and x or x and y you have the same correlation. In this case the correlation is almost zero because we have a very round circle. If the correlation would be higher, we would see that this circle transforms into more like an ellipse, or you could also have negative correlation and the ellipse would just go into the different direction. So this is a very convenient way of visualizing a correlation matrix. Here we see, as another example, a correlated case with very thin ellipses alluding to extremely high correlations. Now the nonlinear case, this was the correlated case. Then we have a nonlinear case where we see that the plane may not fit the data perfectly. If we do our analysis here, we see that the data, the coefficients are partially significant. So not all of them are really significant. You see here that the x, for example, is not significant, y is. But what's very obvious here is that you have a very strong pattern in the residuals telling you that the linear model is not suitable here. The validity of the data is not clear. Shapiro-Wilk tells no, Kolmogorov-Smirnov says yes. The big and challenging question is now what you do in such a case, and we will not deal with that in this lecture. We would just like to sensibilize you that you should not always just fit a linear model. But there are advanced means of dealing with such data as well. Now in reality, you will have big data, many variables, not just x and y, and the first thing you should do is you assess correlations between the variables. So you have this huge correlation matrix, you compute it in exactly the same way as we have done before, and then you see that some of the variables may be correlated and some of them may not be correlated. Now what you can do is some kind of stepwise regression. You say, well, those variables that are correlated, we will take them out. So in order to just spare us the redundancy of very correlated variable, we say we just take the correlated ones away and hope that this already helps. Usually the question which variables do really influence the result cannot be answered so easily. As I said, correlations is an issue, but you may also have nonlinearity in some of the variables, maybe not all. And you may have very strong influences in one variable, which are however not significant due to extremely high variances. So there is something called stepwise regression, where you can give a model and do a stepwise regression which uses the AKA-IKE information criterion, but this is a little too advanced for this course. One must mention that this AKA-IKE criterion is not really best practice, but it's often the thing that is being done. The output of such a regression analysis, unfortunately the data here is confidential, is a list of coefficients which may be significant and coefficients which may not be significant. What's very interesting is the estimate of the coefficients. Mainly interesting is whether it has a negative sign, meaning negative correlation, or a positive sign, meaning positive correlation. This can serve very well as an assessment of whether your model does what your intuition would tell you. What you also see down here is the p-value of the whole model, which usually is significant if you manage to explain some of the variance with some coefficients. Also the multiple r squared, in this case 0.7, is not too low. What you can do is you can look at the residuals. This is always a one-dimensional thing, and in the case of this data set here, you see that you do not have the normality assumption fulfilled. That is due to a not metric variable. The dataset comes actually from a questionnaire with approximately 7 or 8 choices to choose, and this shows in discrete levels when you plot the residuals, and it also shows into not normality of the distribution, which is also captured by the t-test. So in this case, you're really not on the safe side doing a regression analysis. This is very dangerous here. You very well may run into problems concerning model interpretation when you try to do this. So now what can you take with concerning multivariate regression? Well, take with that there is some kind of best practice around, but that you're not aware of how to use it, because there are methods involved that are going a little more far than this course would permit. So the first method of best practice would be a factor analysis or principal component analysis to determine the independent variables. The next step would be stepwise regression or by hand regression, choosing variables and including variables into your model. Such practices are taught in the T4 module in the Master of Life Sciences, also in T3, and in the Plenum course Biostatistics, again in the Master Life Sciences. So this is clearly advanced topics. Now what should you take with for this course? For this course, we emphasize that we will give you data where you can really fit the model with all the factors involved, so you will not have to choose. You should, however, be able to check the assumptions on normality of and structures in the residuals, so the residual plot. And you should be able to check dependency structures of the input variables with the core or the plot core command, and you should then document your findings transparently. Linear regression is a very powerful tool in the end. It is used and applied very often, but please be careful, be transparent with your assumptions and with the steps you're undertaking.